No problem. Yeah.
Right.
So let me
Then,
just get started. So the title of my talk today is Software Technology for Automated Feedback Generation. And it's basically an overview of the work that I've been doing in the last 14, 15 years or so. So short bio of myself. I'm an associate professor indeed for the Open University of the Netherlands. And since this year, January this year, I'm also the head of the computer science department there. But I also have a background and a history at Utrecht University. So I did my PhD in software technology. I finished my PhD in 2005. I've been a junior lecturer for 2 years. I did some master level courses, including type system course and an advanced functional programming course these days at Utrecht University. And since then, I'm also associated as a guest researcher in Johan Jeuring's group. So that's the group of software technology for learning and teaching research group. So most of the work that I'm presenting today is also in collaboration with Johan Jeuring and also other members from this research group, also including Hieke Keuning. So my talk for today is about intelligent tutoring systems, and I do not have enough time to explain you what these kind of systems are, but in case you've never seen these, well, intelligent tutoring systems they are computer systems that provide immediate and customized feedback to learners. So these are the kind of systems that help you to get familiar with all kinds of topics. So one way to look at these systems is to study their structure, so how they are structured, how they are built. And in literature, we typically see that there is this classical architecture which has 4 components that together form an intelligent tutoring system. So on the one hand, we have an expert knowledge module. And this is the part where you code all the expert knowledge about a particular problem domain. So this is all the expertise. If you, for instance, have a tutor in mathematics where all the mathematical knowledge is ending up. We have a student model. So this is the part of the system where you try to model the learner. So what does the student know and what kind of problems does the student have? Then we have a third model, which is a tutoring module. This is where the pedagogical decisions or the didactical decisions are being made. So this is about how are you going to help the learner and how are you going to present feedback and hints and at what particular time, for instance. And then we have the fourth component. This is the user interface module. This is the part of the system in which the student or the learner is interacting with the system. Now, most of the work that I've been doing is in this expert knowledge module. So it's about coding and representing expert knowledge in code so that the system can generate, in our case, automatically feedback out of this. In these kind of systems, intelligent tutoring system, we typically distinguish 2 loops. So if you look at the behavior of an intelligent tutoring system, on one hand, we have an outer loop, and this is about solving one task after another. So important decisions, for instance, in this outer loop is what is the next task that I'm going to provide to a student? What is the next task that is at his particular level? We also have an inner loop, and the inner loop is the kind of steps that you have to take to solve one such a problem. The kind of problems that we study are typically complex multi-step problems, and the inner loop is about providing feedback within such a multi-step problem. So it's about the steps that a student has to take. To give you a more concrete example, this is one of the intelligent tutoring systems we have been developing. This is a tutoring system by Josje Lodder. She did her PhD at Utrecht at Open University, and she was also supervised by Johan and by me. And this is about constructing axiomatic proofs. So here you can clearly see in the interface that on the right-hand side, there is this box where you can select the next step that you have to take, the next rule that you want to apply to finish your axiomatic proof. On the bottom right, you see all kinds of buttons that provide feedback and hints. So if the student is stuck or needs more help, there are all kinds of buttons and options that you can ask for help at any point in time. And on the left-hand side, you see that there's a proof being constructed in a stepwise fashion. In this case, there are multiple solutions that are correct, multiple ways that you can construct such an axiomatic proof. And of course, at every point in time, you can ask for these feedback and hints. So what motivates my research? I think my motivation is to apply software technology to make it easier to construct the kind of intelligent tutoring systems that I just sketched. So we know that the construction of ITSs are very complex. So in literature, it's being reported that there are typically 200 to 300 hours of development time needed to provide just a single hour of instruction for a pupil. And this is, of course, very expensive. And I want to see if software technology can help to make it easier and simpler to construct these kind of intelligent tutoring systems. I'm also studying whether I can use explicit expert domain knowledge to provide better feedback. So to see whether I can generate richer kinds of feedback to learners. And finally, I'm also interested in applying this approach that I'm going to present to you to a wide range of problem domains. Not just for mathematics and logic, but also to all kinds of other problems. So in this presentation, I'm going to briefly present a couple of techniques from software technology that I have been using to build these kind of intelligent tutoring systems. And these techniques are rewrite strategies for generating automated feedback. I'm going to say a bit about embedding lightweight rewrite rules in these kind of systems. And I'm going to say a bit about generic traversals over terms that we have in these intelligent tutoring systems. So the approach that I'm going to sketch has been tried and implemented on several problem domains. So here you see a collection of PhD theses, some of them very recent, about our techniques being applied to specific problem domains. So from left to right, we have an intelligent tutoring system that helps you construct an Haskell program, a functional program, and provide feedback on this. Then we have the PhD thesis by Josje Lodder. She made a collection of all kinds of tutoring systems for logic. So axiomatic proofs, propositional logic, inductive proofs. We have a third PhD thesis by Hieke Keuning. She studied code refactoring for imperative language. And the last PhD thesis is from the Freudenthal Institute by Sietske Takoma. And she studied how to generate intelligent feedback in a university statistics education course. So you can see these are very diverse problem domains, and well, they're all based on one and the same technique. The technique that's behind it, that's a framework, a software framework. It's called the IDEAS framework. And this is what we use as the basis for all these kind of tutoring systems. It's developed in Haskell. It's over 12,000 lines of code. And well, it's the basis for most of our software that we develop. The first technique of today is rewrite strategies. So what are these kind of rewrite strategies? They are problem-solving procedures. So what we did is we designed a domain-specific language in which you can very concisely specify problem-solving procedures for a particular domain. These problem-solving procedures, they describe sequences of rules that you have to apply in order to solve a particular task. And there's all kind of semantics behind it. I'm not going to present it today. They are based on a trace-based semantics, which is kind of similar to the communicating sequential processes that have also been popularized by Tony Hoare. And in this domain-specific language, we have a very small set of core combinators, but there are all kinds of new operators in which you can compose these problem-solving procedures to form more complex procedures. So for instance, the interleaving of procedures or topological sorts of these kind of procedures. Based on these problem-solving procedures, we automatically generate the feedback. And you can think of all kinds of different feedback that we can generate from these problem-solving procedures. For instance, to recognize the solution strategy that a learner is following, we can detect detours. So if someone is doing steps that are, well, not smart at this particular point in time, we can suggest subgoals, provide next steps, provide worked out examples, etc. So let's make this a bit more concrete. So suppose that we have a very simple propositional logic language, and that the goal is to rewrite a particular formula into negation normal form. So negation normal form means that you are going to push the negations inside the formula until they end up near the atoms. So on the left, you see an example of a worked out solution where you can see that you can apply the Morgan law twice and then apply a double negation before reaching a proposition formula that is in negation normal form. So one of the things that is strategically important if you are going to do this strategy is that you should always push outermost negations inside first, because in general, this will result in fewer steps in reaching the solution. So for these kind of tasks, you can write a rewrite strategy in our strategy language. And this would look like the expression that I wrote down on the right-hand side. So in this case, there are 3 rules that you can apply: double negation, the Morgan OR, and the Morgan AND laws. And you can compose these 3 rules with the OR combinator, which is denoted by a vertical bar surrounded by 2 dots. This is the OR combinator, so this denotes alternatives. You can choose between the 3 rules. Now we want to apply these 3 rules somewhere inside the formula. And for this, we can use the once top-down combinator, which tells you that you should, in a top-down fashion, try to apply these kind of rules. And you have to repeat this strategy until no rules can be applied anymore. And this is what the repeat combinator is doing, that is on the outside. So this is the kind of rewrite strategies that we formulate. And based on this, we can automatically generate all kind of interesting feedback messages to learners. So this is just an overview of the most important strategy combinators that we have in our language. So we have sequence. You should first do strategy P and then do strategy Q. We have a primitive combinator that denotes success. So you're done. You don't have to do anything. We can have choice over 2 strategies, so either P or Q. But we can also express preference. So P is preferred over Q. So if you have to generate a hint, first try to generate something using strategy P, and if this does not work, generate something for Q. This is subtly different from the left bias choice combinator that we also have in our language, which says something like you should do P, and only if this is not possible, you should try to do Q. Now, based on this set of very simple strategy combinators, we can define all kinds of derived combinators. So for instance, we could try to apply a strategy S, which is basically the same as saying you should do S, or else you should succeed. And also the repeat combinator that I used in my example on the previous slide can be expressed in terms of this try combinator and just recursively using the repeat combinator in the following. So this is very neat. We can create a very rich combinator language based on just a few primitives. Of course, we can use recursion in our language, but we can also make the recursion more explicit. For this, we can use the fixed point combinator that we also have in our language. The advantage of the fixed point combinator instead of having a recursive call to the combinator is that we can have a finite representation of the strategy. You can see the definition with this fixed point combinator on the right hand side. And the advantage now is that we can do all kinds of interesting things with the representation of the strategy. For instance, extracting rules from the strategy, we can tweak it, we can customize it a bit, or we can even visualize these kind of strategies. And this works because we have a finite representation. Okay, so this was a very quick overview of just a strategy language, a domain-specific language, and we have all kinds of interesting extensions on top of this strategy language that help us to define these kind of strategies. So the first thing that I'm going to present now is how you can also embed the rewrite rules. So these are the laws that you, for instance, want to have in this strategy. So if I go back to my example for proposition logic, you could imagine that I have this data type. It's a very simple, straightforward data type for representing proposition formula in Haskell in this case. So what we have is a proposition is either a conjunction of two logical formulas, it's a disjunction, it's the negation of a formula, or it's just a variable, in which case I'm going to represent it as a string. This is the example that I'm going to work with, but these kind of representations can become very complex, and it can also be nested with all kinds of other data types. So for instance, if I look at a typical expression that you would have in secondary school or high school mathematics, you would perhaps have equations such as 3 times x plus 9 equals 0 or x equals 1. So there you can see that I have expressions, I have equations, and I also have a logical connector, in this case, a disjunction. So these data types are more complex. So the techniques that I'm going to present also have to cater for these more complex representations. And of course, in the axiomatic proofs that I presented or that I showed you earlier, it's also a much more complicated representation, a much more complex data type that is being used under the hood. Now, embedding these kind of rewrite rules is surprisingly simple in our case, because on the top right, you can see the 3 laws for proposition logic, double negation, and the 2 De Morgan laws. And in Haskell, these can be embedded with some magic as normal functions. And this is, I think it's a very neat trick. So the laws, they have meta variables, phi's and psi's, that are representing arbitrary propositions. And in our representation, in our embedding in Haskell, you can use lambda abstractions for this. So I'm going to represent a formula as a lambda function, where I'm going to introduce, in this case, the phi and the psi, using the normal scoping mechanism that is in Haskell. And as you can see, these rewrite rules, they have a left-hand side and they have a right-hand side in this case. Now the question in this case is, because it's now a function, I can represent this, but how can we use such a rewrite rule? How does this work? The answer is that there's a lot of machinery and a lot of tricks that are being used in this rewrite rule function that you can also see on this particular slide. So what we use behind the scenes is a generic approach, a generic programming approach. So what we do is we convert this data type, this logic data type that I showed, to a generic term data type that also has support for meta variables. So we have these 2 functions, a conversion function from my logic data type to this generic term data type. And I have a conversion function the other way around, which goes from a term data type back to a proposition logic. And this is a partial function. This is a function that may fail, hence the maybe that you can see in the type signature, because not all terms represent valid logical propositions. They can also represent other things. So intuitively, the 2 are each other's inverses. And the trick that we are now going to do is we are going to define all kinds of interesting functions on this term data type. And because of the 2 conversion functions, we can also lift this functionality back to our, in this case, our logic data type. I don't have to write these two functions by hand. They can be derived automatically from the data type generation using standard Haskell technology. So for those of you who are familiar with generic programming techniques, there are far more powerful generic programming libraries that do not rely on these explicit conversions to this term data type. They can also provide more type safety, etc. But for us, this works. This is sufficiently a solution. So the advantages of this representation that I now have is that I can do all kinds of interesting things based on this rewrite rules that I can define as I just showed you. So I can do all kinds of interesting analyses on these rules. For instance, Knut Bendix completion, which tries to make a set of rewrite rules to confluent in this case. I can also use AC rewriting for these kind of rewrite rules. So that's rewriting modulo associativity and commutativity, which is very important if you are in a domain which has associative and commutative operators. I can inverse rules, going back the other way around if I want. I can do automated tested. I can do documentation of these kind of rules, all because I have an explicit representation of the rule that I can work with. So I just sketch it, but the summary of the rewrite rules that I presented is that it's indeed helping me to simplify construction. It's very lightweight notation. It even looks a bit like the law that I'm specifying. It has an explicit representation which helped me to generate better feedback, and it is problem domain independent. So I can indeed use it for many different problem domains. This was one technique. The other technique is about generic traversals. Generic traversals, well, if I have a proposition formula like the one on the sheet, I can look at it from a tree representation, of course. And the idea is now that I'm also going to maintain a point of focus, which is also called sometimes a cursor. So this is the subterm that I'm currently considering, and this can be very easily be implemented using a so-called zipper data structure over my generic term data type. Now I have 5 navigational actions, 5 things that I can do given such a cursor within my tree. I can go up to my parent node, I can move left and I can move right to my sibling, or I can visit one of my children. If I go down, I visit my first child. If I go use down last, I visit my last child. And with these 5 navigational actions, you can of course traverse over full trees and yeah, basically reach every point in the tree. These actions may fail. So depending on what your current position is, you may not be able to go up, for instance, if you're in the root. And there are all kinds of interesting rules that you can think of. For instance, if you go left and then you go back right again, this is more or less the same as the identity function. Similarly, if you first go down and then you go up, this is also more or less the identity function. And I say more or less because, of course, actions may fail. Slide. This also gives rise to a very natural encoding of the position in such trees. And this position is just useful for generating feedback later on. Now, the last thing that I want to show you is how you can use these very simple primitive navigation actions to create more complex traversals or more complex visits. And for this, I'm going to use the strategy combinators that I presented in the beginning of my presentation. So the first thing that I'm going to present to you is a horizontal visit. So the idea of a horizontal visit is that you have to focus on the first child and that you are going to visit all your siblings from left to right. the visit one combinator is such a horizontal visit, and the idea is that you're going to apply a strategy S, and you're either going to apply it to the current position, or you're first going to the right and then recursively apply the visit one strategy combinator to the rest of the tree. Similarly, you can have visit first combinators, which tries to visit the first node, first child on which the strategy S succeeds, or you can also define combinators that visit all children from left to right. Now, if we have these horizontal visits in place, we can also think about one layer visits. So a layered visit basically means that you first go down, then you're going to do some actions, a horizontal visit, and then in the end you're going to go up again, ending up in the same node as where you started. So for instance, the layer one combinator is using the visit one combinator, so that's the visit just one of the children from left to right, using just one layer. Now the final step that I have to show you is how you can also have a full layered visit, so just not one layer, but arbitrary many layers. And for this, what we need is yet another fixed point. So if you want to apply a strategy somewhere, this means that you are going to apply the strategy here, or you're going to apply the layer one strategy combinator to the procedure, but then in a recursive fashion. Now, this is just a handful of combinators that you can build out of these navigational actions, but there are all kinds of more interesting and more complex combinators that you can build, including full traversals, spine traversals, innermost traversals, outermost traversals, etc. So if I look at an example trace, this is the example that I started with. You can actually see the corresponding trace if this strategy is being executed, and you can also see that the navigation actions going down and going up and going right, they end up in our trace, which also means that I can use this to generate feedback to learners. So just a quick summary again for these generic traversals. Again, they are first class strategy combinators, so they are very simple to use, and you can just use them together with other strategy combinators. Also nest these traversal combinators, no problem. They are again explicitly represented in our strategy language, which allows for all kinds of interesting opportunities for feedback generation, and they are domain independent. So I can use these combinators for all the problem domains in my introduction, whether this is programming, logic, or mathematics. So just to conclude, I think I'm going to skip over the trends and the challenges. The thing that I presented is a couple of techniques from software technology that we are using to build these intelligent tutoring systems. I've presented rewrite strategies. They are used for feedback generation. I have shown you how rewrite rules, they are the laws that you are applying, the steps, the basic steps, how these can be embedded in a language such as Haskell in a quite elegant way. But under the hood, we have to do a lot of data type generic programming to make this work. This is kind of the hidden magic that you do not see, but that is there in the framework. And I've also shown you how generic traversals can be composed. And they can be used within these rewrite strategies. And they also introduce all kinds of interesting new strategy combinators for your recipes. The presented approach can be and is applied to a wide range of problem domains, which is of course also very helpful and nice. So this was my presentation. I'm open for questions. If there are more questions afterwards, please send me an email or visit the project website. So thank you for your attention.
Yeah, thank you, Bastiaan. Are my headphones working now? Can you hear me?
I can hear you, yeah.
Okay, very good. So, of course, I should, as a chair, first give other people opportunity to ask a question. Okay, I see there is something in the chat. No, that's not a question, that's just applause. Okay, so first of all, thank you for your talk, and thank you also for being very precise to stay in the time. I think I stole 2 minutes at the beginning, and you exactly took those 2 minutes, and rightly so. I have a few questions, namely, so I feel that, so as I understand, you have, of this tutoring system, you have several components, and one of these components is to give feedback to the student. And all these rewriting is in order to rewrite the feedback in different ways. Okay, good. Just that I get on the same page. And then can you use these tutoring systems also for less formal tasks? So for instance, you talked about statistics, which is usually considered a part of mathematics.
Yeah.
But I could also say, oh, I want to have a writing exercise for my students about scientific writing, or I want to have an exercise about how to write nice code. And it's not that the code is correct, that may be easy, but maybe I want to have some, I teach them something about how to write code in a modularized way. Oh, there are many tasks that are less formal, right, and more fuzzy.
Yeah.
Do you
Yeah.
think that these systems are applicable to these settings as well?
Perhaps. But the problem is, of course, that you still need expert knowledge about how to solve something stepwise. And of course, this is straightforward to formalize for domains such as logic, proposition logic, high school mathematics. These are the very easy domains. The domains that you now see on the slide, they are advanced, they are complex, they are troublesome. There are 4 PhD that defended their thesis and spent 5 years just studying these kind of topics. So these are at our current limits. But of course, the question is, yeah, how much more informal can you get? So for instance, in the domain of software design, if we're talking about UML diagrams, it's already getting a bit more complicated than the kind of domains that you see here, or in processing natural language. But then we also get into the problem of eliciting the expert knowledge from the experts. So what are the steps? What is correct? What is not correct? This needs to be formalized somehow in these kind of systems. And I would argue that for these less formal domains, it's also going to be more complicated to formalize this. I hope this answers your question.
Yes, yes, yes. This is going along what I expected. I have a kind of silly remark. I guess you said 3x plus 9 equals 0, so I guess x must be minus 3 then?
I think so, yeah.
Okay, okay, good.
Don't know where it is, yep.
And maybe this is, I guess, a somewhat annoying question, but you mentioned a lambda function. And now I haven't studied computer science, and many people tell me there's this lambda function, but of course, I know lambda is a Greek letter, and that's not very descriptive, and it's used in many different contexts.
Yeah, it's just an anonymous function. Maybe this is a better name. So the thing that I'm introducing here, the thing that I'm writing here is just an anonymous function. So if I take the De Morgan end rule, for instance, the thing that I'm defining there is an anonymous function that takes 2 parameters. So it's a phi and a psi. And based on this, it produces a result. That's the thing on the right-hand side. And the lambda is just a notation, an anonymous lambda or an anonymous function that you can also use in Java, for instance. Okay. But it's just a function.
Yes, yes. So I think mathematics is all over the place where they use a certain letter for something, and then this letter suddenly becomes that thing. Let's say E or pi, and at some point we cannot use any letter anymore because they all have predefined meanings.
Yeah.
So since I didn't see a question in the chat, let me post the Gather link. So for people who are interested in hanging out with colleagues, and Bastiaan, maybe you have a little bit of time, or meeting you personally, then maybe we can do that. And otherwise, I would thank you again for the talk, and nice to have got to know you and a little bit of your research. And yes, I guess I stopped the video and then I go to Gather and hope to see some of you. goodbye.
Okay, and thank you for the opportunity. Bye-bye.
Hoi Wouter en Bastiaan.
Dag Jeroen.
Het enige die nog over zijn, ik zie dat ik me heel stom vergist heb, want ik dacht het begint om 16:30, maar ik zie nou op mijn agenda dat het de eindtijd is. Dus
Foei.
ik denk van, zijn ze nou al met de vraag bezig?
Ja.
Het is opgenomen, zie ik.
Het is opgenomen, dus dat is, ja. En ik zit te kijken of er ook nog ergens een chat is, want die kan ik volgens mij niet zien.
Ja, dus ik zag in de uitnodiging stond er een hangout waar dan dat...
Ja, ik vind hem waarschijnlijk wel.
Ik heb hem hier staan, dus ik kan hem even naar de chat kopiëren, dan kan je hem...
Volgens mij zie ik de chat niet. Ik ben gast bij jullie. Dus dat is denk ik het probleem.
Maar die chat wordt überhaupt niet gebruikt. Of dat kan ook niet bij een colloquium talk, geloof ik. Maar in ieder geval, er is nou een after meeting in Gather.town. Heb je die wel?
Ja, dan ga ik daar nog even naartoe.
Daar hangen ze uit.
Zeker.
Oké, nou, ik ga de video kijken. Ja. Sorry.
Wouter waarschijnlijk ook. Ja, die is ook al.
Wouter is ook al vertrokken. Ja.
Ja.
See you.
Hoi.